The darkness is not empty. It is full. A plenum of potential, a canvas of creation stretched to a taut, infinite smoothness, waiting, and against this profound and whispering dark, against the velvet negation of absolute nothingness, a singular point of light persists. It is a humble luminescence, a subtle breach in the absolute black, a delicate puncture in the fabric of the night that seems almost apologetic in its faintness. It does not demand attention. It does not blaze with the imperial arrogance of Sirius, the dog star whose diamond-hard gleam has guided desert caravans and marked the flooding of the Nile for millennia. It lacks the commanding, geometric presence of Orion's belt, that celestial yardstick around which winter myths and stellar nurseries swirl. It is not part of the sprawling mythic sweep of the Milky Way's core, that river of crushed diamonds and stardust that arcs across the zenith, the backbone of night itself. This point holds no prominent place in the pantheon of constellations that have guided navigators and inspired poets since the dawn of conscious thought. It claims no ancient lineage in the Epic of Gilgamesh or the Odyssey of Argo. It resides instead in the lesser-told stories of the southern celestial hemisphere, a modest point within the obscure constellation of Centaurus, the half-man, half-horse of Greek legend, forever charging across the star fields. To the unaided eye, under skies unsullied by the electric glow of human civilization, it reveals itself not as a singular entity, but as a soft, unresolved smudge, a gentle blur of stellar presence that ancient astronomers, from Ptolemy to the sky watchers of the Andes, perceived as one star, a single note in the harmonic scale of the heavens. It is a light that asks for patience, for a quieted mind and a willing gaze, a surrender of the need for instant, dazzling revelation. It is an introverted star, and in return for our contemplation, it offers not spectacle, but a silent, profound promise. That promise is one of adjacency, of kinship across the terrifying gulf, of a cosmic doorstep waiting just beyond the frosted boundaries of our own solar dominion, beyond the sway of our sun's gravity and the reach of its light. Within that faint, steady glow resides a narrative of such depth and grandeur that it encompasses the entire life cycle of stars, from their gravitational birth in cold molecular clouds to their eventual, quiet or violent demise. It holds the gravitational choreography of celestial bodies bound in complex, multi-million-year dances. It contains the fervent, scientific hope for other worlds, for landscapes under alien suns, and the nascent, trembling ambition of a species, young and fragile, daring to consider the voyage not as metaphor, but as future engineering. It is a story written not in ink or on parchment, but in the fundamental physics of nuclear fusion, the relentless, perfect geometry of elliptical orbits described by Newton and refined by Einstein, the patient, finite, and unyielding speed of light traveling through the vacuum, and the enigmatic, probabilistic possibilities of chemistry becoming biology under the gentle or harsh light of other suns. It is the story of our closest cosmic neighbor, and in its telling, we inevitably tell the story of ourselves, of our place, and of our potential destiny among the stars. For generations, for millennia, we have mapped the continents of our own world, named its mountains and its seas, traced the courses of its rivers and the boundaries of its deserts. We have even, in a burst of transcendent effort in the latter half of the 20th century, walked upon the dusty, desolate plains of our own moon, leaving footprints in sterile regolith and looking back at the marble of Earth, a whole world hanging in the black. Yet, through all those acts of territorial acquisition and local exploration, a part of our collective consciousness, a thread of wonder woven into the fabric of human thought, has always been turned outward, toward that particular, unassuming point of light in Centaurus. It has been a cosmic neighbor whose windows we have never seen into, whose gardens we have never glimpsed, a presence felt rather than known. We have wondered with a mixture of disciplined scientific curiosity and a deeper, more primal longing, what and who might be looking back from those distant shores. Is that faint glow the campfire of another intelligence, a sentient gaze meeting ours across the light years? Or is it merely a brilliant, mindless furnace, heating silent rocks in a sterile void? The question haunts our science and our art. The journey to understand it, to truly know it, begins not with the roar of rocket engines or the crackle of mission control communications, but with a far more fundamental and humbling act, a quiet, unflinching acknowledgement of our own place in the cosmic order, a recalibration of our sense of home and distance. We are, for the moment, inhabitants of a single star system. We reside in a vibrant, noisy, troubled, and breathtakingly beautiful oasis of life and mind orbiting a modest, middle-aged yellow dwarf star we call the Sun. Our world, Earth, is a dynamic sphere of water and rock, swathed in a thin, fragile film of gas, the atmosphere that we call our sky. This biosphere, this zone of life, is a mere whisper on the surface of the planet, a delicate layer thinner in proportion to the globe than the skin of an apple. Within this layer, all of our stories, our wars, our loves, our art, our empires and their ruins, our symphonies and our silences are contained. It is all sheltered by a magnetic field generated by the churning of molten iron in the planet's core, a force field that deflects the solar wind and warmed by the steady, reliable fusion reactions of our star, located 93 million miles away, a distance we have canonized as the astronomical unit, the fundamental ruler of our local cosmic neighborhood. And just beyond the gravitational hills and valleys of our own solar backyard, beyond the orbit of the outermost dwarf planets and the icy debris of the Kuiper Belt, just past the theoretical influence of the Sun's gravity and the bubble of its magnetic influence, the heliosphere, a mere stone's throw in the incomprehensible metric of the galaxy, lies another system. The distance to that point of light is our first and most enduring lesson in cosmic humility. It is a distance that does not merely stretch the imagination, it shatters our terrestrial frameworks of geography and endeavor, rendering our proudest journeys insignificant, our fastest vehicles glacial. That light we see tonight, that soft smudge in Centaurus, is 4.37 light-years distant from our solar system. To translate this unit, this measure of the cosmic, into the familiar language of human journeys is to immediately feel the vertigo of scale, the disorienting awe that comes from true perspective. A light year is not a measure of time, but of distance. It is the distance that a photon, a particle of light, traveling at the universe's ultimate speed limit of 186,282 miles per second in the vacuum of space, covers in one Earth year. It is a span of approximately 5.88 trillion miles. Therefore, the distance to our nearest stellar neighbor is 4.37 multiplied by that staggering figure, approximately 25.6 trillion miles. A trillion is a number we use in economics and cosmology but rarely truly feel it is a 1 followed by 12 zeros. 25 such trillions with 600 billion miles besides. The number is so vast it ceases to be a distance and becomes an abstraction, a mathematical monument to our isolation, a silence expressed in numerals. To comprehend it, one must engage in a series of mental reductions, comparisons that inevitably fall short but hint at the truth. Consider the greatest voyages of our species, the journeys that expanded our mental map of the world. The circumnavigation of the globe by Magellan's expedition, a journey that transformed human understanding of the planet from a flat disk to a spherical body, spanned roughly 40,000 miles over 3 harrowing years. The distance to our nearest stellar neighbor is over 600 million times that length. 600 million Magellan voyages laid end to end would be required to bridge the gap. Consider the Apollo missions to the Moon, that 250,000-mile journey that represented a giant leap for mankind. You would need to make that journey back and forth over 50 billion times to equal the distance to Alpha Centauri. Consider our fastest human-made objects, the Pioneer and Voyager probes, those silent, golden record-carrying ambassadors of the 1970s, now drifting beyond the heliopause into the true interstellar medium. They travel at speeds exceeding 38,000 miles per hour, a velocity that allowed them to reach Jupiter in months and Saturn in years. Speeds that seemed godlike in their day. Yet, at such a seemingly tremendous speed, a journey to this nearest star would demand over 70,000 years of relentless, unswerving travel through the void. 70 millennia. This is an expanse of time that stretches from the dawn of modern humanity, from the caves of Lascaux and Altamira, where our ancestors painted visions of bulls and horses with ochre and charcoal, through the entire rise and fall of the Egyptian, Greek, Roman, and every subsequent civilization, through the Middle Ages, the Renaissance, the Industrial and Digital Revolutions, and far into a future we cannot envision, a future where languages we speak would be dead, cultures we know would be dust, and the very ship itself would be a relic. All of recorded human history, and much more, would fit within the single-minded silent voyage of a tiny craft coasting through the endless night, carrying no living crew, only the ghost of the civilization that launched it. This is the first, most formidable truth of interstellar aspiration. The universe is constructed on a framework of space and time that renders our conventional notions of travel, of journeying from point A to point B, quaint, almost childish in their ambition. The scales are not just larger, they are of a different order of magnitude entirely. We are to the galaxy as a microbe is to a continent, and the distances between continents for the microbe are effectively infinite. This vastness imposes another, more subtle but equally profound condition on all our knowledge. The very light by which we see this star system tonight is not a contemporary report, not a live transmission of its current state. It is a message from the past, a historical document carried by photons that have journeyed undisturbed for over 4 years through the interstellar medium, brushing past dust grains and magnetic fields, but essentially unchanged since the moment they leapt from the star's photosphere. The light that enters the eye of an observer in the present moment departed from that star system when our ancestors were mastering the use of fire, painting on cave walls, and telling the first stories under these very same but differently configured stars. We are, in this act of looking up, receiving an ancient dispatch. The system we perceive is not as it is, but as it was over 4 years ago. This inevitable lag, this delay between event and observation, is the fundamental condition of all cosmic observation, a permanent reminder of the finite speed of light and the tyranny of distance. It is a law of cosmic communication. To look outward into space is always, without exception, to look backward in time. We are archaeologists of the present, sifting through the ancient light of celestial objects to piece together their histories. We see the Sun as it was 8 minutes ago, Jupiter as it was over 40 minutes ago, and Alpha Centauri as it was over 4 years ago. This temporal dislocation means we study a version of Alpha Centauri that is already over 4 years into its future, a future about which we remain, for the moment, blissfully and necessarily ignorant. Any event that occurred there, a stellar flare, a planetary collision, the flickering on of a city's lights, has not yet reached us and will not for years. Our knowledge is always historical, always retrospective. We live in the past of the universe. Yet, for all its staggering remoteness and the historical nature of its light, this system holds the singular, poignant title of Proxima, the closest. Its name, as bestowed by the systematic catalogues of Western astronomy, is Alpha Centauri. It is the brightest star in the constellation Centaurus, hence Alpha. It is our celestial next of kin, the adjacent apartment in the sprawling, multi-storied high-rise of the Milky Way galaxy, a structure containing over 200 billion such apartments. And within that deceptively simple designation, Alpha Centauri lies not a singular identity, but a complex and dynamic family, a gravitational consortium of profound interest. Alpha Centauri is not a lone solitary sentinel like our Sun. It is a gravitational ballet, a triple star system where 3 distinct suns are bound in an intricate, everlasting dance of mutual attraction and orbital mechanics. A dance governed by the universal law of gravitation, first articulated by Isaac Newton and later refined by Albert Einstein's theory of general relativity. This fundamental fact, its multiplicity, changes everything about the environment, the potential for planets, and the very nature of stability within that domain. Our solar system, with its single stable gravitational focus at the Sun, is a placid, predictable lake, its planets tracing nearly circular, well-separated ellipses. Alpha Centauri is a system of tides and complex currents, where the competing and harmonizing influences of multiple stellar bodies create a far more complex and potentially chaotic environment for any planets, asteroids, or comets that might orbit within its domain. The gravitational landscape is not a simple smooth well, but a dynamic, evolving terrain of hills and valleys where stability is a prized and perhaps rare condition. A delicate balance that must be maintained over billions of years for a planet to offer a stable platform for the evolution of life. The primary actors in this celestial drama are the binary pair, Alpha Centauri A and B. They are the heart of the system, the central couple whose relationship defines the character of the inner realms. The stellar couplet that dominates the visible light from that smudge in the sky. These 2 stars are locked in a mutual gravitational embrace, whirling around a common center of mass like cosmic dancers holding each other in a slow, stately waltz. Their partnership is both intimate and elongated, a gravitational bond that takes approximately 80 of our Earth years to complete a single, full revolution. This is a rhythmic pulse at the core of the system, a metronomic beat that sets the tempo for everything within its sphere of influence. a heartbeat measured in human lifespans. During their elongated orbital dance, the distance between them varies significantly, following the dictates of Kepler's laws of planetary motion, which apply equally to stars orbiting each other. They swing from about the distance from our Sun to Saturn at their closest approach, a separation of roughly 1.1 billion miles, a gap that could comfortably contain nearly the entire inner solar system out to Jupiter, to roughly the distance from the Sun to Pluto at their farthest separation, about 3.6 billion miles. This cyclical pulsing of gravitational influence, this periodic tightening and loosening of their bond, creates a zone of dynamic stability and potential instability, a region where the orbits of smaller bodies can be long-lived and predictable if they find the right resonant harmonies, or where they can be perturbed, altered, or even ejected over astronomical timescales if they stray into the wrong gravitational neighborhood. It is a system breathing slowly in and out over the span of a human lifetime, a cosmic lung whose inhalation and exhalation takes 8 decades. Alpha Centauri A is a star that feels almost familiar, a near twin to our own Sun that offers a profound point of reference, a mirror held up to our own stellar parent. It is classified as a main sequence star, a G-type yellow dwarf, quietly and steadily fusing hydrogen into helium in its core with a serene, stable fury. This process, the proton-proton chain reaction, is the same engine that powers our own Sun, converting mass into energy with relentless efficiency via Einstein's famous equation, E = mc. In the core of Alpha Centauri A, under pressures exceeding 250 billion times Earth's atmospheric pressure and temperatures soaring above 15 million degrees Celsius, protons, the nuclei of hydrogen atoms, overcome their mutual electromagnetic repulsion through quantum tunneling and fuse, eventually forming helium nuclei and releasing energy in the form of gamma-ray photons. These photons then begin a long random walk outward, being absorbed and re-emitted countless times over perhaps 100,000 years, until they finally reach the surface, the photosphere, and leap into space as visible light. Its mass is about 10% greater than our Sun's, and its radius is about 22% larger. These are not trivial differences in the life of a star. They mean its core is hotter, its pressure greater, and its nuclear reactions more vigorous. Consequently, it is about 50% more luminous than the Sun. If we were to replace our Sun with Alpha Centauri A, our sky would be illuminated by a more intense, whiter light, casting sharper, deeper shadows. The Sun, as we know it, emits a gentle, life-giving yellow-white glow with a color temperature of about 5,800 Kelvin. Alpha Centauri A would be a more brilliant, commanding presence with a temperature of about 5,790 Kelvin, almost identical in color but brighter. Its photosphere, the visible surface, churns with a slightly more energetic version of the convective processes we see on our Sun, vast cells of rising and falling plasma, granulation patterns, each the size of a continent, transporting heat from the interior outward. Yet, in the grand taxonomy of the cosmos, among the myriad stellar types, from brilliant short-lived blue giants to feeble, long-lived red dwarfs, it is undeniably a sibling to our Sun, a close cousin in the stellar family tree. Its spectrum, the unique fingerprint of its chemical composition, revealed by the dark absorption lines where elements in its atmosphere have stolen specific wavelengths of light, is remarkably similar. It possesses a comparable metallicity, a similar abundance of elements heavier than hydrogen and helium, the very elements astronomers call metals, the stuff of rocks, planets, and life, carbon, nitrogen, oxygen, silicon, iron. It is a star under which one could imagine, with reasonable scientific plausibility, a similar story of planetary formation from a swirling protoplanetary disk of gas and dust, and perhaps a similar genesis of chemistry, complexity, and consciousness. It represents a known quantity, a beacon of the familiar in the potentially alien architecture of this triple system. Around such a star, the classical habitable zone, where liquid water could exist on a planetary surface, is slightly farther out and wider than our own, a more generous band of potential real estate for life as we understand it. Its partner, Alpha Centauri B, presents a study in subtle contrast, a different stellar temperament within the same stellar household. Slightly smaller and cooler, it is classified as a K-type orange dwarf. Its mass is about 90% that of our Sun, and its diameter is about 14% smaller. It burns its nuclear fuel with a quieter, ruddier, more ochre glow with a photospheric temperature of about 5260 Kelvin, giving it a distinctly orange hue compared to its yellowish companion. But one must not mistake its diminished physical dimensions for gentleness or placidity. Alpha Centauri B possesses a more restless, magnetically active nature. It is a star known for its heightened stellar activity, which manifests in a more turbulent and extended corona. The superheated outer atmosphere visible during solar eclipses, and significantly a greater proportional output of X-ray and ultraviolet radiation than its larger, calmer companion. This is a critical detail with profound implications for potential habitability. High-energy X-ray and ultraviolet radiation are the great scourges of nascent and established planetary atmospheres. They can break apart molecules, ionize atoms, and over geological time, strip away an atmosphere entirely through a process called atmospheric erosion, leaving a world barren and exposed like Mars. A hypothetical planet orbiting within the traditional habitable zone of Alpha Centauri B, that notional band where temperatures might allow for liquid water on a surface, would be subjected to a more punishing stellar wind and more frequent energetic bursts of high-energy particles from flares and coronal mass ejections. This could pose a formidable, though not necessarily insurmountable, challenge to the development and sustainability of a fragile biosphere. Life there would need robust defenses, perhaps a thick atmosphere like Venus's to absorb the radiation, a strong planetary magnetic field like Earth's to deflect the charged particles, or a subterranean or aquatic origin, using rock or water as a shield. The binary dance of A and B is thus a dance of opposites and complements. The brighter, steadier, more solar-like A and the smaller, more volatile, magnetically restless B. Their gravitational interplay does not merely define their own paths, it sculpts the environment around them, creating zones of stable resonance and zones of chaotic instability, a complex gravitational melody within which any planetary systems must find their harmonic or be cast out into the darkness. And then there is the third member of this family, the one whose name literally means nearest, a name that speaks not of brightness or dominance, but of simple, stark location, Proxima Centauri. It is here that the story shifts dramatically from the familiar to the extreme, from solar twins to the most diminutive and populous class of star in the cosmos. Proxima is a main sequence red dwarf, an M-type star, the most common, frugal, and long-lived class of star in the Milky Way galaxy, comprising perhaps 75% of all stars. It is a diminutive, miserly ember of a star. Its mass is a mere 12%, that of our Sun, a threshold barely sufficient to ignite and sustain the steady fusion of hydrogen. Its diameter is only about 1/7 that of the Sun, making it only slightly larger than the planet Jupiter, though with vastly greater density and internal energy. Its luminosity is a pathetic fraction of our Sun's, only about 0.0017% of the Sun's total output, over 20,000 times fainter. To the naked eye, it is utterly invisible, lost in the combined glare of its brilliant siblings and the general wash of the Milky Way's starlight. It is so intrinsically faint that it was not discovered until 1915 by the Scottish astronomer Robert Innes, who identified it as a high proper-motion star, a star moving quickly against the background, and deduced its proximity, a testament to its obscurity despite its extraordinary physical proximity to us. Proxima Centauri is not merely a star. It is a lesson in stellar longevity, tenacity, and cosmic patience. Because its gravitational crush is so much gentler, its core burns its hydrogen fuel at such a miserly frugal rate through a process involving catalysts like carbon, nitrogen, and oxygen. The CNO cycle, which becomes more efficient at higher temperatures, it will live for trillions of years, far outlasting every other star in the galaxy. While stars like our Sun will exhaust their core hydrogen in roughly 10 billion years, swelling into red giants before shedding their outer layers and cooling into white dwarfs, Proxima will continue its faint, steady glow. It will be a dim red beacon, shining long after stars like our Sun and even the Alpha Centauri binary have burned out, faded into stellar cinders, and grown cold. Its orbit around the central pair is so vast, so mind-numbingly huge, that a single circuit takes over 500,000 years, perhaps as long as 600,000 years. We are speaking of an orbital period that encompasses the entire history of Homo sapiens, from our earliest tool-using ancestors on the African savanna to the present day of skyscrapers and satellites, and far beyond into an uncharted future. It is a distant, quiet, and cold outpost of the system, a far-flung companion held by a gravitational thread of astonishing length and weakness, currently orbiting at a distance of about 13,000 astronomical units from the central binary, over 400 times the distance from the Sun to Neptune. Yet, by a quirk of celestial geometry in its immensely long elliptical path, it is currently the closest of the three stars to our own solar system, lying about 4.24 light-years away, slightly closer than the binary pair's 4.37 light-years. It is our true next-door neighbor, a faint, flickering candle in the adjacent cosmic window, a whisper of fusion in the silent night. The environment around a red dwarf like Proxima is fundamentally, radically different from that of a Sun-like star. Its habitable zone, that theoretical band where incident stellar energy might allow for liquid water to exist on a planetary surface, is incredibly close in, shockingly intimate. For Proxima, this zone lies at a distance of only a few million miles from the star's surface, about 0.05 astronomical units, so close that a planet residing within it would complete an orbit in a matter of Earth days, not years. At such intimate proximity, the gravitational and tidal interactions between star and planet become intense and transformative. The most likely, almost inevitable outcome is tidal locking, where the planet's rotation period becomes perfectly synchronized with its orbital period, much like our moon is locked to Earth, always showing the same face. This means one hemisphere permanently faces the star, bathed in eternal, unwavering daylight, while the opposite hemisphere is turned away, shrouded in perpetual, frozen night. This creates a world of radical, permanent extremes, a planet divided against itself, a global geography of here and there that never changes, a world without a day-night cycle as we know it. Furthermore, red dwarfs, especially in their tumultuous youth, which can last for billions of years, are notoriously tempestuous. They are prone to frequent and massive stellar flares, sudden magnetic reconnection events that can double or triple the star's brightness in minutes, blasting out torrents of ultraviolet and X-ray radiation and hurling colossal clouds of charged particles, coronal mass ejections, into space. For a planet huddling so close, within spitting distance of the star, such an event is not a distant astronomical spectacle. It is an atmospheric and surface cataclysm, a potentially sterilizing blast of energy that could scour the surface, break down complex molecules, and strip away any protective gaseous envelope over geological time. To imagine life arising and persisting in such a system is to imagine life under a constant state of siege, finding a niche in an environment of profound extremity, where the very star that provides the energy for life is also its greatest potential executioner, a capricious god that both gives and takes away with violent indifference. Yet, in August of 2016, the astronomical community and the watching world were electrified by a discovery that transformed Proxima Centauri from a curious stellar footnote into arguably the most compelling address in the entire galaxy. Using the exquisite, painstaking method of radial velocity, which detects the subtle rhythmic wobble of a star induced by the gravitational tug of an orbiting planet, researchers at the European Southern Observatory, using the HARP spectrograph at the La Silla Observatory in Chile, announced a monumental finding, Proxima B, the closest known exoplanet to Earth, a world, not a theoretical possibility, not a statistical probability from Kepler data, but a measured reality, a gravitational handshake felt across the void. The data, accumulated from years of precise observations that measured the star's velocity with an accuracy of better than 1 meter per second, roughly walking speed, painted a tantalizing, if necessarily blurry, first portrait. Its minimum mass is estimated to be about 1.07 times that of Earth, and its inferred density, though poorly constrained, suggests a rocky terrestrial composition, not a gaseous mini-Neptune. It is, in the most fundamental architectural sense, an Earth-sized planet, likely made of rock and metal, a cousin in form, if not in circumstance. It orbits Proxima Centauri at a distance of just 7.5 million kilometers, completing a frenetic year every 11.2 Earth days. And by the foundational calculations of orbital dynamics and stellar luminosity, it resides squarely within the star's classical habitable zone. The raw numbers on a slide in a presentation suggest a stunning, almost poetic possibility, a temperate rocky world, a potential abode for life, located right next door in the cosmic neighborhood, a mere stone's throw away on the galactic scale. But the physical reality, as dictated by the harsh, unforgiving physics of red dwarf planetary systems, is infinitely more complex, challenging and nuanced than the simple, comforting phrase habitable zone implies. Proxima B, given its proximity to its small star, is almost certainly tidally locked. Let us endeavor to envision this world, to move beyond abstraction and into the realm of imagined experience, guided by physics and planetary science. On the day side, the star hangs motionless in a sky that is likely black, or perhaps a deep, somber purple, absent the Rayleigh scattering that blues our own atmosphere, because the star's light is predominantly red and the atmospheric composition, if any, would be different. It is a swollen, dull red orb occupying a significant portion of the heavens, a sullen, broiling disk about 10 times larger in angular diameter than our Sun appears from Earth. But this quiet visage is a lie, for periodically, without warning, sections of that disk would erupt in violent, blinding flares, surges of white light that would momentarily drown out the constant red glow, followed by onslaughts of lethal radiation and particles. The surface temperatures on this permanent day side, critically dependent on the presence and composition of an atmosphere, could range from hot enough to melt lead to, if an atmosphere exists with sufficient greenhouse effect, perhaps even hotter, a global desertscape of cracked, glowing rock and simmering dust, bombarded by relentless stellar winds and ultraviolet flux. It is a panorama of fire and fury. On the opposite night side, the view is one of absolute, profound desolation. No star, no sliver of direct light from Proxima, just the permanent, cold glitter of the Milky Way's band, and perhaps, if the atmosphere is thin or absent, the distant, paired jewels of Alpha Centauri A and B, seen as two distinct, brilliant stars in the profound black, a reminder of the broader stellar family. Here, in the endless night, temperatures would plunge to hundreds of degrees below 0 Celsius, a global cryogenic wasteland where any atmosphere the planet might possess would condense and fall as perpetual snow of nitrogen, oxygen, or carbon dioxide, creating a frozen, airless tomb of ices. It is a panorama of ice and stillness, a freeze so deep it is almost absolute. Between these two hellish extremes, however, lies a narrow, twisting ribbon of possibility, the terminator line, the twilight zone, the region of perpetual sunrise or sunset that never progresses to day or night. Here, the star perpetually sits on the horizon, a permanent, half-submerged crimson ball casting long, unmoving shadows. In this band, if conditions are right, temperatures could moderate to a range compatible with liquid water. If Proxima B possesses a substantial atmosphere, a monumental if, its circulation patterns would strive valiantly to redistribute heat from the scorching day side to the freezing night side. This could create a latitudinal belt of potentially temperate conditions, a world without the global seasons as we know them, dictated by axial tilt, but with fierce, permanent climatic gradients driven by the unceasing engine of atmospheric and oceanic heat transport. Perhaps vast sluggish oceans exist here, their surfaces perpetually shrouded in global banks of mist and cloud, warmed from one side and cooled from the other, generating planet-wide weather systems of unimaginable scale and persistence. The coastlines, the boundaries between day and night hemispheres, would be places of immense, never-ending storms as superheated and supercooled air masses collide in a permanent hurricane zone, a ring of fury encircling the globe. The land, if it rises from these twilight seas, would be a place of strange, creeping shadows that never change, where the light is always low, ruddy and diffuse, and where the horizon is defined not by the movement of a sun, but by the slow creep of geology, the rise of mountains, the erosion of valleys, and the endless, complex dance of atmosphere and condensation. If life were to emerge, persist, and even thrive in such a constrained and violent niche, It would be life sculpted by evolutionary pressures we can barely imagine, life that has rewritten the rulebooks of biology. Photosynthesis, if it evolves, would operate at the very limits of quantum efficiency. Plants, or their alien analogues, would need to be masters of photon capture, evolving photosynthetic systems that utilize not the broad spectrum we see, but the specific, dim, red-shifted light of their sun. Their leaves might not be green, reflecting the mid-spectrum light abundant on Earth, but perhaps deep black or violet, saturated with pigments designed to harvest every precious scrap of energy from the faint glow. These would not be fluttering, deciduous things responding to seasons, but likely low, sprawling, mat-like and hardy extremophile forms, perhaps with waxy, reflective, or even metallic coatings to deflect damaging ultraviolet radiation during the star's frequent tantrums. The rhythm of life would not be tied to a reliable daily cycle of light and dark or annual seasons, but to the erratic and violent pulse of stellar activity. Life might adopt a burrowing existence, retreating underground or beneath protective ice sheets to weather the flares, only to emerge in the relative calm afterward. Or it might exist primarily in deep oceanic waters, using the water column as a shield against the worst of the surface radiation, communicating and navigating through bioluminescence in the eternal gloom. It would be a biology of resilience, patience, and profound adaptation, a testament to life's stubborn ability to cling to the most tenuous of opportunities in the face of cosmic hostility, to find a way in the narrowest of margins, to turn a prison into a home. The ultimate habitability of Proxima B hinges on several fragile, interlocking factors, the most critical being the twin guardians of a living world, a magnetic field and a robust atmosphere. The relentless stellar wind and frequent, savage flares from Proxima Centauri pose an existential, erosive threat. Without a global magnetic field, like Earth's magnetosphere, to act as a shield, deflecting and channeling charged particles away, the atmosphere would be steadily eroded away, molecule by molecule, over millions of years, stripped by the stellar wind. This is widely believed to be the fate that befell Mars, a smaller world whose internal dynamo ceased billions of years ago, leaving its atmosphere vulnerable to sputtering loss into space, transforming it from a potentially warmer, wetter world into the cold, thin-air desert we see today. Proxima B, being roughly Earth-sized, might very well still possess a molten, churning metallic core and thus a functioning magnetic dynamo generated by the convective motion of an electrically conducting fluid, likely molten iron in its interior. If it does, this invisible protective force field could be the guardian of its potential biosphere, cradling an atmosphere and deflecting the worst of the stellar onslaught, just as Earth's magnetosphere does. The presence of a substantial atmosphere, in turn, is crucial for so much more than just pressure. It is the medium for temperature regulation via the greenhouse effect, the vehicle for the cycling of elements like carbon and nitrogen, the blanket that prevents all water from either boiling away or freezing solid, and the vast chemical laboratory where simple molecules can interact, driven by energy from the star or the planet's interior, to form the prebiotic compounds that are the precursors to life. Detecting and characterizing the atmosphere of Proxima B is one of the foremost, tantalizing challenges in modern astronomy. A task that pushes our technology to its absolute limits and will require the next generation of space telescopes, like the planned Habitable Worlds Observatory or the extremely large telescope on the ground, to even begin to sniff the chemical composition of its air from across the light years, looking for the spectral signatures of water vapor, oxygen, methane, or other biosignatures. And Proxima B, we are learning, is not alone in its orbit around the dim red star. Further observations, requiring even more painstaking precision, have hinted at a more complex, richer planetary system emerging from the data. There is growing evidence for a second world, dubbed Proxima C. This appears to be a more massive body. A world with a minimum mass several times that of Earth, orbiting much farther out, at a distance of about 200 million kilometers from its star, farther than Mercury is from our Sun. With a year lasting over 5 Earth years, this world resides in a deep, profound freeze, far outside the classical habitable zone. Its true composition remains unknown, but its mass suggests it could be a mini-Neptune, a gaseous world with a thick primordial hydrogen-helium envelope surrounding a rocky or watery core, or perhaps a super-Earth, a large, rocky planet with a frozen, ocean-covered surface beneath a dense, cold atmosphere of gases like nitrogen, methane, or carbon dioxide. Its surface temperature in the feeble glow of Proxima would be lethally cold, likely hovering hundreds of degrees below 0 Celsius, a realm where even atmospheric gases would condense into liquids and solids, a world of exotic ices and crushing pressures. Then there is the tentative detection of Proxima D, a whisper of a world even closer to the star than Proxima B. With a minimum mass, perhaps only a quarter of Earth's, it is a small scorched marble, orbiting so close that its year is a mere 5 Earth days. Its surface, if it has a distinct surface, and is not a globe of molten magma, would be a blistering inferno, certainly tidally locked and utterly sterilized by proximity and radiation. Together, these worlds, confirmed and candidate, sketch the outline of a fascinating, if extreme, miniature planetary system, a hot, tiny inner world, a potential temperate, Earth-sized world in the habitable zone, and a cold, more massive outer world. It is a skeletal architecture reminiscent of our own solar system's layout, inner rocky worlds, outer giants, but compressed and reshaped by the faint, tempestuous nature of its star. It is a testament to the ubiquity and versatility of planet formation, a process that appears to operate around stars of all sizes and temperaments, filling the galaxy with an astonishing diversity of worlds, from hot Jupiters to super-Earths to ocean worlds and perhaps Earth-like gems. The Alpha Centauri system, however, is not solely the domain of Proxima and its intriguing planets. The central binary, the Sun-like stars A and B, have long been prime candidates in the imagination of scientists and science fiction writers for harboring planets of their own, perhaps more Earth-like in their conditions, more familiar in their rhythms. The gravitational dance of two stars complicates the elegant picture of planet formation derived from single-star systems like our own, but it does not preclude it. Sophisticated orbital dynamics models and simulations suggest that planets can indeed form and persist in stable orbits for billions of years within such systems. They could be S-type orbits, circling closely around one of the stars individually, much like planets in our solar system circle the Sun. For such a planet to be stable over billions of years, it typically needs to orbit within about 1/5 of the distance to the other star's gravitational influence, a region known as the Hill sphere. Alternatively, planets could exist in P-type or circumbinary orbits, tracing a wide path that encompasses both stars, like the fictional planet Tatooine from Star Wars, though these require a greater distance from the binary pair to remain stable. The search for planets in the habitable zones of both Alpha Centauri A and B is an ongoing, delicate and high-stakes pursuit, a task made challenging by the sheer brightness of the stars, which drowns out the faint signals of small terrestrial planets. The method of transit photometry, which looks for the minuscule dimming of a star as a planet passes in front of it, is difficult here due to the precise orbital alignment needed and the confounding factor of stellar activity and the binary eclipses. The radial velocity method, which succeeded for Proxima B, must disentangle the planet's tiny wobble from the far larger wobble induced by the stellar binary orbit itself, a feat of data analysis akin to hearing a whisper in a hurricane. Yet, the potential reward is astronomical. A rocky planet of Earth-like mass in the habitable zone of Alpha Centauri A would experience conditions remarkably similar to our own home, albeit under a slightly brighter, hotter sun. The length of its year would be different. Its sky would feature a brilliant secondary sun, B, that would appear as an incredibly bright star, sometimes closer, sometimes farther, casting complex shadows and possibly affecting climate through periodic variations in insolation. But the fundamental parameters of liquid water, moderate temperatures, and a stable gravitational environment could be met. A similar planet in the habitable zone of Alpha Centauri B would have to contend with that star's greater magnetic activity and a slightly redder, dimmer light, but would still orbit within a stable temperature regime where liquid water could theoretically exist on its surface. The discovery of such a world, a true Earth analog around a sun-like star next door, would be a monumental event in human history, offering not just a subject of study, but a tangible, long-term goal, a potential second home in the most profound existential sense, a backup for the biosphere, a new chapter for humanity. The possibility that the Alpha Centauri system contains not one, but multiple worlds of profound interest, a trinity of stars potentially hosting a family of diverse planets, some possibly habitable, some exotic, elevates it from a compelling target to the most compelling target for future exploration that humanity has ever identified in the cosmos. This brings us to the immense, daunting, and ultimately inspiring challenge that lies at the heart of this narrative. The journey itself. To cross the 4.37-light-year gulf with current conventional propulsion technology is, as we have seen, a multi-generational epic spanning geological time, a task so vast it defies contemporary political, economic, and biological frameworks. The workhorses that took us to the moon are utterly useless for such a task. Their specific impulse, a measure of efficiency, is far too low, and the amount of fuel required to accelerate even a small payload to a meaningful fraction of light speed would be astronomically impossibly large, requiring more mass than exists in the observable universe for any appreciable payload, a consequence of the tyrannical rocket equation. More advanced concepts, studied in theory and in limited experiments since the mid-20th century, offer potential but still Herculean challenges. Nuclear thermal propulsion, using a fission reactor to heat a propellant like hydrogen to extreme temperatures before expelling it, could potentially double or triple the exhaust velocity compared to chemical rockets. Nuclear pulse propulsion, The audacious idea behind projects like Orion would use a series of controlled nuclear explosions behind a spacecraft to push it forward via a massive pusher plate and shock absorbers, a concept that could theoretically reach a few percent of light speed and cut the travel time to Alpha Centauri to a few centuries. But such vessels would be monuments of engineering, requiring the construction of massive shock absorbers and radiation shielding, and they would still necessitate closed ecosystems lasting for generations, a profound sociological, psychological, and biological challenge for any crew, essentially requiring a self-sustaining ark carrying a human civilization in miniature across the void, a fragile bubble of biology in an infinite desert. The dream of practical, human-relevant interstellar travel demands a paradigm shift, a leap into realms of physics and engineering that feel, for now, like the outer edge of science fiction. Yet, on that razor's edge between contemporary science and visionary engineering, a bold, elegant, and conceptually simple idea is taking shape, moving from the pages of scientific papers to funded research and development, Breakthrough Starshot. Conceived and funded as a serious research and engineering initiative by the Breakthrough Initiatives Foundation, its stated goal is to prove the feasibility of ultra-fast, light-driven nanocrafts. The concept is as simple in principle as it is staggeringly complex in execution, requiring breakthroughs across half a dozen fields of advanced technology, from materials science to photonics to nanotechnology. Imagine a spacecraft not much larger than a postage stamp, a gram-scale silicon chip dubbed a star chip. This chip would contain, in hyper-miniaturized form, all the essential systems of a probe, cameras smaller than a grain of salt using metasurface optics, photon thrusters for minute course corrections, a nuclear beta-voltaic or laser-powered power supply, navigation sensors, and a laser communication system with a tiny laser and a meter-scale light sail that also serves as an antenna. This tiny craft is attached to a light sail, a meter-sized but incredibly thin sail made of a material like graphene or molybdenum disulfide, only a few hundred atoms thick, engineered to be highly reflective, incredibly lightweight, and able to withstand immense accelerations and the heating from an intense laser beam. The revolutionary aspect is the propulsion system, which is not on board the craft at all. It remains anchored in our home system, presumably on Earth or in orbit. A ground-based array of immensely powerful lasers, a light beamer, possibly spanning a square kilometer or more, would focus its coherent phased energy onto the light sail as the tiny craft is deployed, perhaps from a mothership in high Earth orbit. For several minutes, this concentrated photon barrage, amounting to gigawatts or terawatts of power, the output of a large nuclear power plant focused into a beam, would push against the reflective sail. In the airless void, photons carry momentum, and reflecting them imparts a force, a manifestation of light pressure, a gentle force, but one that, when applied by a beam of such intensity, becomes titanic. This laser-driven photon pressure would accelerate the nanocraft at forces tens of thousands of times greater than Earth's gravity, a brutal, crushing acceleration. But the nanocraft, having no fragile human occupants and being constructed of resilient, nanoscale materials, could theoretically withstand it. Within those few minutes of furious acceleration, it would be boosted to a significant fraction of the speed of light. 20% is the ambitious target. At that velocity, approximately 134 million miles per hour, the probe would reach the Alpha Centauri system in just over 20 years of travel time. It would not carry fuel to slow down, Slowing down from relativistic speeds is an even greater challenge than acceleration, requiring a similar laser array at the destination, which we do not have. It would be a flyby mission, a blazing fast encounter lasting only hours, perhaps minutes, as it streaks through the target system at a significant fraction of light speed. But in those fleeting precious hours, its suite of miniaturized instruments would collect a torrent of invaluable data. Direct, close-up images of the planets, resolved into actual landscapes, not dots. Spectroscopic analyses of their atmospheres and surfaces from up close, measurements of magnetic fields, dust density, and particle environments. This data, collected over a cosmic instant, would then be stored and transmitted back to Earth on a faint, precisely aimed laser beam, a journey of information that would take another 4.37 years to traverse the Gulf and reach our waiting receivers, likely a network of large radio telescopes like the Square Kilometre Array. The engineering challenges standing between this vision and reality are, to put it mildly, monumental. They encompass creating a laser array of sufficient power, coherence, and ability to focus through Earth's atmosphere if ground-based, which may necessitate a space-based array. Designing a light sail material that can reflect over 99.99% of the incident laser light to avoid vaporizing from absorbed heat, and that can withstand the acceleration stresses without rippling or tearing, maintaining a perfect optical figure. Sensitive electronics from the intense cosmic radiation and impacts from interstellar dust grains during the decades-long cruise, a single grain, even a microscopic one, traveling at 20% light speed, would carry the kinetic energy of a speeding bullet, enough to vaporize a portion of the craft. Developing power sources that can remain operational and reliable for half a century in the deep cold of interstellar space with no possibility of repair. And, perhaps most difficult of all, designing a communication system small and light enough to fit on a gram-scale chip, yet powerful and precise enough to beam its precious data across 4.37 light-years to waiting receivers on Earth. A signal so faint it will be buried in noise, requiring extraordinary error correction and detection techniques. These are not merely incremental improvements on existing technology. They require foundational breakthroughs in material science, photonics, nanotechnology, and communications theory. Yet, and this is the inspiring kernel, the fundamental physics permits it. There is no law of nature, no principle of relativity or quantum mechanics that explicitly forbids such a mission. It is a challenge of engineering, of resources, of international cooperation, and of human will. Starshot represents a specific philosophy for interstellar exploration that our first purposeful steps into the interstellar ocean may not be taken in giant, ponderous, multi-generational arcs carrying fragile human bodies and all the life support they require, but by our intelligence and our curiosity, encoded in microscopic silicon and propelled by light, traveling at speeds our biological forms could never endure, sent as scouts, as extensions of our senses, to report back on what lies in the adjacent cosmic valley. It is a philosophy of sending our minds, if not our bodies, first. The arrival of such a probe, even a silent, flashing, momentary passage, would mark a historic turning point in the history of our species and of cosmic awareness. For the first time, an artifact of human conception and manufacture, however tiny, would enter another star system. It would cross the threshold from being a local solar system phenomenon like the Voyagers, which are now interstellar but were not sent to any specific star, to being a purposeful interstellar object, a visitor to a named destination. The images and data it returns would not be the fuzzy dots of light we see through telescopes, or the abstract, beautiful but indirect graphs of spectral data. They would be landscapes, vistas, realities. We might see for the first time the cloud patterns and continents of Proxima B, the crescent of its dayside glowing a sullen red, the terminator line rendered sharp with mountain ranges and valleys, the night side perhaps dark but speckled with the glow of volcanic activity, or, in the realm of the fantastical yet possible, the lights of cities. A thought that ignites the imagination with equal parts hope and trepidation. More likely, the data would reveal a geologically complex but biologically silent terrain, a world of fascinating extremes, but no signs of technology. We would see Alpha Centauri A and B not as a single blurred point, but as true, distinct suns, perhaps with their own families of planets, resolved into tiny disks or crescents. We would map asteroid belts, cometary clouds, and the detailed structure of the dust rings that often surround stars. This torrent of direct information would transform these points of light, these subjects of scientific papers, into places with real geography, weather systems, and geological history. It would tell us with direct evidence if the habitable zones we calculate are truly inhabited by life, or if they are beautiful, empty deserts, planets where the chemistry never made the leap to biology, or where it did and was later extinguished. It would provide a definitive answer to the ancient haunting question of whether we are alone in the universe, at least in our immediate stellar neighborhood. And depending on the answer, that data packet, arriving 4.37 years after the flyby, would either contain the most profound, civilization-altering discovery in human history, evidence of another living world, or it would deliver the most profound loneliness, confirming that in our local cosmic desert, the flame of life burns only here, on this pale blue dot, a solitary, fragile candle in the immense dark. Either answer is transformative. Either answer forces a re-evaluation of our place and our significance. But the human spirit, with its deep-seated drive for direct experience, for the feel of alien soil underfoot and the sight of an alien sky with living eyes, is not ultimately content with mere robotic flybys. No matter how revolutionary, a quiet undercurrent in our collective consciousness, in our myths and our science fiction, to one day set foot on an alien world, to feel its gravity as a personal sensation, to breathe its air or don a suit to walk upon its surface, to look up at its sky and see unfamiliar constellations, to be there in person. The moment a human being, born of Earth, steps onto the surface of Proxima B or a planet of Alpha Centauri A will be the moment the definition of humanity expands irrevocably, fracturing its old terrestrial shell. We will have become, indeed, and not just in theory, an interstellar species. No longer confined to the cradle of a single star, our destiny will have been physically extended to another solar system. That individual, or those individuals, standing on that foreign soil, will look up at a sky where the constellations are utterly unrecognizable, where the patterns of stars are skewed into new arrangements by the parallax of a different vantage point. Our sun will be just another moderately bright star in an alien pattern, perhaps part of a new constellation named by those pioneers for their home or their mission. They will see, clearly visible, the brilliant binary of Alpha Centauri A and B if they are standing on a moon of Proxima, or the faint ruby pinpoint of Proxima if they are on a world of the central binary. Earth will be a pale blue dot, visible only through a telescope, a memory and an origin point, a place of history and nostalgia viewed across a gulf of years as well as miles. The psychological, philosophical, and even spiritual weight of that moment is immeasurable. It will be a second Copernican revolution, but this time not a theoretical displacement from the center of the universe, but a lived, experiential expansion of the human domain. We will know in our bones and in our blood that we are not of a single world, but of many stars, that our destiny is written in the galaxy at large, that we have taken the first step into a larger reality. The challenges of such a human voyage are, of course, exponentially greater than those of a nanocraft. They involve the monumental task of sustaining complex human life for decades or even centuries in the absolute void, protecting fragile biology from the constant, deadly bath of galactic cosmic radiation, high-energy atomic nuclei from supernovae, and the occasional micrometeoroid impact, creating and maintaining perfectly self-sustaining closed ecological systems within a vessel, a miniature Earth in a bottle, for generations. Recycling every drop of water, every molecule of oxygen, every nutrient, and solving the colossal problem of propulsion, not just for acceleration, but for the equally difficult maneuver of slowing down upon arrival after a journey at relativistic speeds. Concepts like induced hibernation or torpor for crew, reducing metabolic rates to extend lifespan and reduce resource consumption, generation ships where those born en route live and die knowing only the ship as their world, their culture evolving in isolation, or enormous world ships with rotating sections for artificial gravity, vast internal parks, and agricultural biomes are the stuff of deep theoretical study, speculative engineering, and science fiction. The energy requirements for accelerating any mass carrying humans to even a few % of light speed are astronomical, likely requiring space-based infrastructure like orbiting solar power satellites or fusion reactors we have not yet built, or the harnessing of antimatter, the most energy-dense fuel conceivable, though its production and containment remain far beyond our current capabilities. The social structures required to maintain a stable, healthy, purposeful society on a voyage spanning centuries are untested and fraught with psychological peril. The perils of isolation, genetic diversity, leadership, and purpose over timescales longer than any civilization has remained coherent. Yet, if we survey the long arc of our species' history, it is a history of overcoming barriers that once seemed insurmountable, of redefining the possible. We crossed unknown oceans on rafts and in wooden ships, guided by stars and courage, not knowing what continents or oblivion lay on the other side. We learned to fly, to break the sound barrier, to leave our atmosphere entirely, each step a defiance of previous limits, each achievement a platform for the next, a new normal from which to gaze at the next horizon. The journey to Alpha Centauri, in all its terrifying difficulty, is the next, greatest, logical step in that ancient lineage of exploration, the ultimate maritime voyage on the ocean of space, the longest journey our kind has ever contemplated. For now, in this early 21st century, Alpha Centauri remains a distant dream, a subject of intense scientific study, a point of light tracked by telescopes, and a goal that lives more in papers and conferences than in shipyards. It is the closest of the hundreds of billions of stars in our galaxy, a concrete named destination in a cosmos of infinite, anonymous possibility. Its study is the perfect training ground, the prototype for the new sciences of comparative exoplanetology and interstellar travel planning. Every new detail we glean about its stellar dynamics, its potential planets, its circumstellar dust, and its radiation environment is a piece of the map we are drawing, a chart for future generations who will attempt the crossing. It teaches us firsthand about the diversity of stellar systems, challenging our sun-centric assumptions. It shows us the resilience of planets, forming and surviving in complex gravitational environments. It forces us to consider the potential niches for life in conditions we once thought utterly forbidding, expanding our understanding of life's tenacity and the sheer inventiveness of evolution. In the grand, slow-motion timeline of the cosmos, spanning over 13.8 billion years from the Big Bang to the present, our awakening to the profound significance of Alpha Centauri is a very recent event, a flicker of consciousness in the dark. A mere century ago, we did not know for certain if planets existed around other stars. It was a matter of philosophical debate. A single generation ago, the planet Proxima B was unknown, undetected, its existence not even a confirmed speculation. Today, we are actively planning, however tentatively and with long-term horizons measured in decades, how to send our first purposeful robotic envoys, our scouts made of light and silicon, to that very point of light. The arc of progress, while agonizingly slow on the scale of a single human lifetime, is breathtakingly swift on the scale of cosmic discovery and technological evolution. We stand at the precipice of a new age, looking across a gulf that seems both infinite and, for the very first time in our history, potentially bridgeable by our own ingenuity, by the application of mind to matter. The stars next door are no longer just points of light in a mythic tapestry. They are destinations with names, with characterized environments, with mysteries begging for direct investigation. Their story is now inextricably intertwined with our own story of curiosity, ingenuity, and the unquenchable desire to see what lies over the horizon, to push beyond the familiar warmth of our sun, to venture into the great silent dark between the stars, to answer the call that has echoed in the human soul since we first looked up and wondered. This desire is perhaps the deepest mandate of life that has evolved to the point of comprehending the universe, to explore, to know, to reach out. And when we finally arrive, whether in the form of a silent, speeding chip of silicon transmitting its findings, or in the living, breathing flesh of our distant descendants, we will have crossed more than just a spatial gulf. We will have crossed a fundamental threshold of being, an evolutionary Rubicon. We will have become citizens of the galaxy, our fate and our future, written not solely in the soil of one world, but in the light of many suns. Our story is part of a broader stellar narrative, our consciousness a thread in the cosmic tapestry. For now we watch, we learn, we dream. We train our telescopes on that faint point in the southern sky, collect its photons and decode its secrets. We look to that gentle glow and know that there, in the silence and the flares, in the tidal locked twilight and the binary waltz, lies our first great challenge and our first great hope beyond the cradle of home. The universe is vast beyond comprehension, and we are small, a fragile film of biology on a pale blue dot, a momentary spark in the long night. But we are beginning to learn, to stretch, to reach out with the tools of our mind and the long arm of our technology, to touch the universe beyond our doorstep. And in that reaching, in that striving across the light years, we are slowly, surely, redefining what it means to be human. We are the universe contemplating itself, and we are taking our first tentative steps to meet our neighbors, to extend the family of sentience, to plant a flag not of territory but of awareness in the soil of another star. Good night.